In the previous episode, elliptic curves became groups. We learned how to add points, multiply them by integers, and identify torsion subgroups. Now we introduce the maps that connect different elliptic curves, isogenies. These maps preserve the group structure, their kernels control them, and the difficulty of recovering them is one of the central ideas behind isogeny-based cryptography. From now on, we work mainly with elliptic curves over finite fields. The set of rational points E of FQ is finite, but it still forms an abelian group. An isogeny will be a map from one elliptic curve to another that respects this algebraic structure. For cryptographic problems, the most important setting will eventually be supersingular elliptic curves over fp squared. An isogeny from E to E' is a non-constant algebraic map that sends the identity point of E to the identity point of E'. For elliptic curves, this condition forces the map to be a group homomorphism. In other words, phi of p plus q equals phi of p plus phi of q. So an isogeny is simultaneously geometric and algebraic. This homomorphism property means that an isogeny preserves every relation among points. Orders, torsion subgroups, and repeated addition all pass through the map. Isomorphisms are exactly the isogenies of degree 1, but most isogenies identify several source points and therefore lose some information. The kernel of phi is the set of source points that map to the identity of the target. Because phi is a homomorphism, the kernel is a subgroup of E. Visually, all of these points are collapsed to one point by the map. The kernel measures exactly where the isogeny fails to be injective. For a separable isogeny, the degree is simply the number of points in its kernel. A degree 2 isogeny has two kernel points, including the identity. A degree L isogeny has a kernel of order L. In positive characteristic, there can also be an inseparable part, but the cryptographic isogenies we evaluate as small prime steps are normally chosen separable, with degree coprime to the characteristic. Degrees behave perfectly under composition. If phi has degree m and psi has degree n, then psi composed with phi has degree m times n. This simple identity will become crucial. It tells us that a map of enormous degree can be represented as a sequence of much smaller maps. For example, composing a degree 2 isogeny with a degree 3 isogeny produces a degree 6 isogeny. The order of the maps matters, but the degree of the composition is always the product. Before using Frobenius, let us define it. Over a field of q elements, the q-power Frobenius map raises each coordinate to the qth power. It sends a point x, y to x to the q, y to the q, and it fixes the point at infinity. In general, the target is the Frobenius twist E superscript q. When the curve itself is defined over fq, the twist is the same curve, so Frobenius is an endomorphism of E. A subgroup G is called Frobenius stable when applying pi q permutes the points of G. That is the condition we will use to know that a quotient isogeny is defined over the original finite field. Here is the theorem we need. Let E be an elliptic curve, and let G contained in E of k be a finite subgroup. Then there exists an elliptic curve, denoted E modulo G, and a separable isogeny phi from E to E modulo G, whose kernel is exactly G. What does the quotient mean intuitively? The map collapses every point of G to the identity. More generally, it collapses every translate P plus G to a single point. So P and P plus Q have the same image whenever Q belongs to G. You can think of the quotient as gluing together exactly the points that differ by an element of G. Now suppose psi from E to E' is any separable isogeny with kernel G. Because psi kills G, it has the same value on every coset P plus G. Therefore, psi first passes through the quotient map pi G, and then through an isomorphism from E modulo G to E'. Symbolically, psi equals iota composed with pi G. That is the precise meaning of the phrase, the kernel determines the isogeny. It determines the quotient isogeny, uniquely up to an isomorphism of the target. Intuitively, once you know exactly which points are being glued together, you know how the curve is being folded. The only remaining freedom is the coordinate system used to draw the output curve. Over a finite field, if G is stable under the Frobenius map we just defined, then the quotient curve and quotient isogeny can be defined over that same base field. The quotient theorem tells us that the isogeny exists. Vélu's formulas tell us how to write it down. Their input is the kernel, the finite list of points that must be collapsed. Their output is an explicit equation for the target curve E modulo G and explicit rational functions for the map. The intuition is simple. Start with the old coordinates and add correction terms, one for each non-zero kernel point. These corrections are engineered so that every point in G maps to the identity, and so that points in the same coset receive the same image. In short, knowing the kernel lets Vélu reconstruct the entire isogeny. When the kernel is small, the sums are short, so reconstruction and evaluation are fast. That is why small-degree isogenies are our basic computational building blocks. For degree 2, the kernel contains the identity and one non-zero point. Vélu's sums therefore contain only one non-trivial term. For degree 3, the kernel contains the identity, a point t, and its negative, so there are only two non-zero terms. Degrees 2 and 3 are particularly simple, but the same principle works for any small prime L. We can now state the computational problem. Given two elliptic curves that are known to be isogenous, find an explicit isogeny between them. In supersingular cryptography, the input is typically two supersingular curves over fp squared, and the desired output may be a rational map, a kernel, or equivalently a path made of small-degree isogenies. A small but important qualification: two completely arbitrary random elliptic curves need not be isogenous. We pose the problem inside a fixed isogeny class. For supersingular curves over an algebraic closure, this gives a particularly rich connected world of curves and isogenies. The asymmetry is now clear. When the kernel is known and manageable, Vélu's formulas let us reconstruct the isogeny efficiently. But when we are given only the two endpoint curves, recovering a connecting isogeny appears much harder. The generic supersingular isogeny problem is believed to resist both classical and quantum computers at suitable parameter sizes. We should be precise. This is a hardness assumption, not a proof that the problem is impossible. Quantum algorithms provide meaningful speedups, but no general polynomial time classical or quantum algorithm is known for random generic instances. This assumed hardness is the foundation of isogeny-based cryptography. Why not simply compute one direct isogeny between two random curves in the same supersingular class? The field characteristic P is cryptographically enormous, often hundreds of bits. The supersingular isogeny graph contains on the order of p vertices. A typical root using degree L edges has length on the order of log base L of p. Because degree multiplies, the composite isogeny has degree L to the power L, which is polynomial in p. That sounds modest when written as p to a constant power, but p itself is larger than 2 to the 256. Writing or evaluating a single rational map of that total degree would be completely impractical. Instead of materializing one enormous rational map, we represent it as a chain of small-degree isogenies. Each step has a tiny kernel, so it can be reconstructed with short formulas and evaluated efficiently. The output curve of one step becomes the input curve of the next. The total degree is still the product of the step degrees, but the representation stays compact. A degree is called smooth when all of its prime factors are small. Isogeny-based constructions are designed around chains whose degrees are powers or products of small primes, such as 2, 3, 5, or 7. Here is the episode in one picture. A finite subgroup G gives a quotient curve E modulo G and a separable isogeny with kernel G. Any other separable isogeny with the same kernel differs only by an isomorphism of the target. Vélu's formulas reconstruct the explicit map from that kernel. The forward construction is efficient, while recovering a hidden connecting path from its endpoints is believed hard. And instead of expanding one enormous map, we store it as a chain of small-degree isogenies. In the next episode, these chains become paths in the isogeny graph. Curves will be vertices, small-degree isogenies will be edges, and the hard problem will become a path-finding problem through a vast expander graph. That graphical viewpoint will make the cryptographic structure much easier to see. Thanks for watching.